So now let's consider beta smooth case. So when there is no constraint, the main ingredient to show the 1 over t convergence speed was this inequality. And for gamma is equal to 1 over beta, from this inequality we have fxt minus fxt plus 1 is greater than or equal to 1 over 2 beta gradient of fxt normed square. And since this is always positive, this is always greater than or equal to 0. So we can always say that fxt plus 1 is less than or equal to fx star. So we can guarantee that every iteration improves the objective function. We can be closer to the optimal solution as we do more iteration. Okay, that's why from the beta smooth function we can guarantee x capital T minus fx star instead of fx bar minus fx star, which was the result for just Lipschitz continuous case. But the problem is here, again, we have to deal with the projection. Now xt plus 1 is yt plus 1, and we have to define xt plus 1 as a projection of yt plus 1. That is the main challenge when we introduce convex constraint set. Okay, so now gamma times gradient of xt is not equal to xt minus xt plus 1. That's the main problem. Instead, in the next slide, I will show this inequality. So this inequality is an alternative inequality for this. So basically almost the same except this part. Okay. Without this part, this inequality exactly this. But because of the projection thing, we need to have this additional term. Okay, good. Right, let's show this sufficient decrease lemma. So first part, from the beta smooth property, we have this inequality. fxt plus 1 is less than or equal to fxt plus gradient of fxt xt plus 1 minus xt plus beta over 2 xt plus 1 minus xt normed square. This comes from beta smooth. And we can rewrite this part using the definition of yt plus 1. And we can rewrite this line by this. Okay. Here I just use the simple trick 2 times A transpose B is equal to A square B square minus A minus B square. Okay. And this line is I just rewrite the previous line by subtracting this term and this term because they are the same. And this line I just use the definition of yt plus 1 minus xt. Okay. When there is no constraint, since in that case yt plus 1 is equal to xt plus 1, so we don't have this term. But since we have constraint set and yt plus 1 is not equal to xt plus 1 in some cases, if yt plus 1 is outside your constraint set, so we need this additional term. Okay. Next one is the lemma 3.6 of Bubeck's convex optimization textbook. This is also very important. When we set the step size gamma equal to 1 over beta and gxt, let's define gxt is equal to beta times xt minus xt plus 1. So this is kind of effective gradient. So which is defined using the true update direction. Then fxt plus 1 minus fy is less than or equal to gxt transpose xt minus y minus 1 over 2 beta gxt norm square for y in your constraint set. Okay, how to show this? We have this equality, we just add fxt and subtract fxt, and this inequality comes from the beta smooth property. This one is the beta smooth property of this, and this part comes from the convex property of this. Okay, and then this one, I just rewrite the previous line. So just combine this one, and I use the definition of gxt. And then we have this inequality. I will explain how to show this inequality in the next slide. I will use the second property of projection. And from this, we can conclude this. Okay? Why? Because the gxt square, norm square, is equal to beta square times xt minus xt plus 1 square, or this is equal to gxt transpose times beta xt minus xt plus 1. Okay, so here we subtract 1 over beta gxt norm square and add 1 over beta gxt norm square. Then in the end we have this. Okay. Now let's show the remaining term, A inequality A. From the first property of projection, we have this one. Okay. So since xt plus 1 is equal to pi x yt plus 1, using this first property of projection, we have this for all y in your constraint set x. So which means this. Okay. So you can replace this one by this. Sorry. So from this, you can conclude this. Gradient of fxt transpose xt plus 1 minus y is less than or equal to gxt transpose xt plus 1 minus y. Okay, that's it. And from this lemma, when we set y is equal to xt, then we have this inequality. fxt plus 1 minus fxt is greater than less than or equal to minus 1 over 2 beta gxt norm square. So again, we can say that fxt plus 1 is less than or equal to fxt. We can guarantee this. So now we can make a result using fxt minus fx star instead of fx bar minus fx star. Now we can have this because of this. So very interestingly, we just replace gradient of fxt by the effective gradient gxt. So here gxt was beta times xt minus xt plus 1. Now we have all ingredient. So using the vanilla analysis, we have this. And from the two lemmas, we have these two inequality for fxt plus 1, fxt minus fxt plus 1. So from this part, we can upper bound this one by fx0 minus fx capital T. And from this property, we can guarantee fxt always can have a better function value as we did more iteration. So we have fx capital T minus fx star is less than or equal to 1 over capital T, T from 1 to capital T, fxt minus fx star. So from this and this, we have this result, fx capital T minus fx star less than or equal to beta over 2 capital T times x0 minus x star square. So again, we have the same convergence speed.